In this video, we're going to look at formal charges and condensed ways to write structural formulas. Okay? All right, so here's the simplest molecule I can think of that has a formal charge, ammonium chloride. Okay, we've probably known for a long time that this is an ionic compound consisting of an ammonium ion and a chloride ion. But you may wonder, let's look at the ammonium ion itself. Where's the charge here? Okay, all right. So if we think about how bonding in lone pairs work, in lone pairs, the atom owns both of those electrons, okay? They're only going to that one specific atom. But in a bond, it's shared between two atoms. So we say that in a bond, it owns half of the electrons that are in a bond. Okay, so you can use this formula right here to calculate the formal charge at any atom. Okay, we're going to take the number of valence electrons in the free atom, subtract from that the number of bonds, which because we're only counting half of them, that works out perfectly. Okay, and we're subtracting from that the number of electrons that are in lone pairs. Okay, so if we look at nitrogen here, there's 5 electrons in a free, 5 valence electrons in a free nitrogen atom. 4 bonds to it. There are no electrons in lone pairs, so when we work this equation out, it's +1. For the chloride ion, there's no bonds here and 4 lone pairs, so there's 7 valence electrons in a free chlorine, no bonds, 8 electrons in lone pairs, and we work this equation out, it comes out to be -1. Okay, so formal charge is primarily just a bookkeeping device. If we want to look at what the actual charge is, we have to also consider the electronegativity of the atoms. So in ammonium ion itself, there really isn't very much positive charge at nitrogen, because even though there's a formal positive charge, the dipole moments of the nitrogen-hydrogen bonds all send the electron density back to nitrogen, so it's compensated somewhat, and there really actually is very little charge at nitrogen. So this formal charge is really primarily a bookkeeping device, and we're going to see in many cases that it actually is a good guideline for reactivity and how sometimes we get reactivity characteristic of the formal charge. Not always, but in a lot of times we do. Okay. All right. So the thing to remember about formal charges is that a lot of atoms don't have formal charges, and these are what we call the normal valence states for various atoms. Hydrogen, 1 bond, no lone pairs. Boron and anything underneath it like aluminum or gallium or indium or whatever, 3 bonds, no lone pairs. Okay, and the thing to note here is that this is the only one where we don't have an octet. Okay, we'll discuss that a little later in the class, but that's the only one. There's no octet for boron. All right, so carbon, 4 bonds, no lone pairs, and silicon and tin would both also feature that as well. Nitrogen and phosphorus, 3 bonds, 1 lone pair. Oxygen and sulfur, 2 bonds, 2 lone pairs. Fluorine and the rest of the halogens, 1 bond and 3 lone pairs. All right, so when we're looking for formal charges, it's always a good idea to know what elements don't have formal charges. So we're going to look for atoms being in these states, and if they are, we're not going to mess with them. We're not going to waste our time doing a formal charge calculation where the answer is going to be 0. Since the uncharged state is the most common configuration for these atoms, this is a table that you have to become familiar with. All right, so let's do a few calculations here. Where are the formal charges in this molecule, and what is the overall charge? Note that in this one, all the lone pairs have been shown, and this is something that has, for this type of problem, I have to draw the lone pairs. All right, so you see a lot of magenta asterisks here as well. These mean these are the atoms that are in their normal valence state and they don't have any formal charge. So we could calculate it in a zero, but the objective of this course is to recognize that this is the normal valence state. So you should know to ignore these atoms. Okay, so it's the other atoms here that we're looking at formal charges. So formal charges are going to be here, 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 and here. Okay, so that first carbon on the far left, no lone pairs, 3 bonds, it ends up having a +1 charge. The far left nitrogen looks like the nitrogen and ammonium chloride, 4 bonds, no lone pairs, +1. This nitrogen right here, 2 bonds, 2 lone pairs, it's isoelectronic with an oxygen, you could say. A formal charge, 5 minus 2 minus 4, and that adds up to -1. By the way, this is about as complex as the math gets in organic chemistry. So if you're a mathophobe, I guess you should be pretty happy about that. And this last one, the formal charge at that sulfur is +1. 6 valence electrons in free sulfur, -3 bonds, -2 electrons in lone pairs, and that gets us to +1. All right, so what's the formal charge? Well, it is actually going to be +2. We have 3 positives and 1 negative. So if we add +3 and -1 together, we end up with +2. Okay? It is conventional in organic chemistry to omit the lone pairs and infer their presence or absence by the number of bonds and the presence or absence of formal charges at each atom. In the early stages of this class, we're going to give you the lone pairs, but be prepared by the end of this class. This is a skill that you're expected to have, that you'll know how many electrons charge lone pair based on, or that you'll know that the number of lone pairs based on the number of bonds in lone pairs for that particular atom. Okay, let's do this one. Assign all formal charges in the following molecule and determine the formal total charge on the molecule. Each fluorine's got 3 lone pairs. We didn't show them. Showing them would make it too messy. So we know that we're not going to have to do formal charge calculation at fluorine. This boron's not right. So we're going to have to do a formal charge calculation there. This oxygen, 2 bonds, 2 lone pairs. No need for a formal charge calculation. Nitrogen with 4 bonds, we've got to do a calculation, and oxygen with 3 bonds, again, we've got to do a calculation to figure out what the charge is. Okay, so I think here's the answer here. Okay, so if we look at the charged oxygen, which is the one right here, 6 valence electrons in a free oxygen, -3 bonds, -2 lone pair electrons, it's +1, so there's a +1 there. The nitrogen, okay, is the only nitrogen we have in the molecule, so there's no confusion as to which one it is. 5 valence count of free nitrogen, -4, -0 is +1. It looks kind of like the ammonium ion in that respect. And boron itself also has a charge as well. 3 valence electrons, -4 bonds, and no lone pair electrons in boron, so it's -1. There are no other atoms with a charge, therefore the charge on this molecule is +1. And this is one way that we could express that. Okay? All right. Let's look at another issue in organic chemistry, and that's how we write structural formulas. Early organic chemists had to communicate their results to each other with a typewriter. So they had to, they couldn't always draw pictures to write papers. They had to devise a way to write structural formulas, and they came up with the idea of a condensed structural formula. All right, so here's fluoromethane right here. All right, so we can write it with the carbons followed by the hydrogens followed by any other atoms attached to that carbon. Okay. All right, let's look at another one. This is ethane. And its structural formula here could be written as just two consecutive CH3 groups. All right, here is ethanol. Okay, so it's a carbon followed by a carbon with an oxygen on it. This is how we would write the condensed structural formula for ethanol. And finally, here's butane. And butane can be written as 4 consecutive carbons. The N carbons have 3 hydrogens. Okay, here's the N carbons right here. They have 3 hydrogens, and the interior carbons shown there each have 2 hydrogens, so we would write it CH3, then CH2, CH2, CH3. All right, if we have a lot of consecutive CH2 groups, a lot of times you'll see them abbreviated in parentheses this way. Either of these is an acceptable condensed structural formula representation for butane. Okay, and finally, when the structure gets really complex, bond-line diagrams are employed. Okay, so many of you have probably seen one particular compound written this way, and this is benzene. Okay. All right, so this compound here is called cyclopentane. We'll take up how to name compounds in the next chapter. But one way to write these 5 carbons in the shape in a ring here, each with a CH2 group, is as the pentagon shown here. Okay, sorry, I didn't need to even show you benzene. It's already there. So this is an acceptable representation for cyclopentane. Okay, benzene can be written this way. And these abbreviated structures that I've shown in circle are referred to as bond-line diagrams. Here's the essence of a bond-line diagram. Each carbon atom is assumed to be the end of the line or the intersection of 2 or more lines. Okay? Hydrogen atoms that are bonded to carbon are not shown. We're just going to assume that every carbon has 4 bonds and that there are enough hydrogens of that particular carbon to make 4 bonds. All heteroatoms, these are atoms that are not carbon or hydrogen, have to be shown. And if a hydrogen is attached to a heteroatom, that has to be shown. Okay? Now, these rules are not rigid. If we need emphasis, want to highlight a part of the molecule, we can take a bond-line diagram and then just draw out parts of the molecule so that we can emphasize it there. Okay? We don't use bond-line diagrams for very simple molecules because when you just, we'll look at some examples of how that's confusing on the next slide. And it's generally a good idea to not use bond-line diagrams for charged carbons because counting the hydrogens plus now accommodating the charge, students make a lot of mistakes when they introduce too many of these shortcuts into the structure. So I would advise you to not use bond-line diagrams in the vicinity of charged carbons. Okay, so let's look at a few examples here. All right, so this compound right here okay, could be reduced to this simple bond line diagram here. Notice that the ends of the lines represent CH3 groups. Okay. All right. And these intersections of lines represent CH2s or CHs or whatever. It represent less than a CH3 group. Okay. All right. So notice how here that we have two oxygens, and we showed both of them. We have one hydrogen that's at a oxygen, not attached to carbon, but attached to oxygen, and that one has to be shown. Okay, all right, here's a couple of illegal pharmaceuticals here, but we'll turn them into bond line diagrams. It's not illegal to do that. Okay, so this is the drug ecstasy. All right, so here it is with all the carbons and hydrogens shown, and it simplifies to the structure here. Again, notice we have two oxygens that we had to show, a nitrogen, and a hydrogen attached to a nitrogen had to be shown. Okay, all right. All right, this is LSD, lysergic acid diethylamide. Okay, and here is the bond line diagram for LSD. Okay, so notice that some of the carbon-carbon bonds are double bonds. One of the carbon-oxygen bonds is a double bond, and we have three nitrogens in here. Okay, and one oxygen. So our one oxygen is there. Our nitrogens, again, are all shown. They're much more prominent in the bond line diagrams. The one hydrogen that's attached to a nitrogen or oxygen, in this case a nitrogen, is shown that way. Okay? Now, sometimes when molecules are really simple, it's not a good idea to use bond line diagrams. Technically, writing a dash is equivalent to writing ethane, but is it ethane or is it a dash? Who knows, okay? Methanol, this compound right here, technically it could be written this way, but again, how do you know it's not dash OH or instead of like the end of the dash referring to a CH3 group? So we would not represent simple molecules like this as bond line diagrams. In extreme, I guess you could just take methane and draw it as a dot, but again, that wouldn't make sense. Okay, so as molecules get larger, they get represented as bond line diagrams, and this is the language of organic chemistry. You have to become familiar with these types of diagrams. If you don't get this down in the early stages of the class, you'll be very confused when asked to do problems and predict reaction pathways. All right, so we're going to end this one with a problem. Let's take the pharmaceutical compound Viagra and see what its molecular formula is. Okay, most of us know the story of Viagra. It's a failed blood pressure medicine that had side effects far more valuable to the pharmaceutical company than the original goal of this. All right, so if we think about this, we have, let's see, several carbons. All right, so there we have some hydrogens. Got a hydrogen and a carbon there. Carbon, 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 hydrogen, carbon, hydrogen, carbon, hydrogen, carbon with two hydrogens, carbon with three hydrogens, Okay, carbon with 2 hydrogens, another carbon that looks kind of like that one, yet another one that looks sort of like that one, and then finally this carbon right here. Okay, I don't know why that one streaked like that. Anyway, I guess I didn't lift the pen high enough off the pad. All right, so this is the molecule that we're looking at. If you look at the carbons, let's just count them. It's kind of a hard exercise to do sometimes, but 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. There's 19 carbons here and a lot of hydrogens. There's 3 on that outside that nitrogen. 4, 5, 6, 7, 8, 9, 12, 14, 16, 18, 20, 23. So our formula, I missed one of the ones that was on nitrogen there, so I have to add that too. So C19H24N6O4S is the molecular formula for Viagra. All right, so this video ends here, and we'll pick up by looking at some other structural issues in the next one. Okay.